Good afternoon, everyone. My name is Sylvain. I am from the Technical University of Munich, and today I will be presenting our work enabling cross-study comparison, a framework for automated BIM-Qa evaluation. This work has been done together with Stefan Fuchs, Stavros, Nousias, and André Borrmann, who are also in the room today. So very brief now, we have talked enough about it today. What is BIM-Qa? It's just a way for a human to ask a question using natural language and have a system that is looking somehow for the answer inside the BIM model and output an answer in natural language. And why this is useful is because most of the people who actually need to access information are not the ones spending their whole life in Revit or in other BIM viewing software. If you take asset managers, construction managers, and so on, even for the projects who have a BIM model, they may be opening the viewer once a week at best. And so it's very hard for them to navigate through all of the drop-down menu, hamburger menu, and so on, that you will need to be able to answer very simple questions like the one listed here. And because of that, we have seen, today is a good example, we have seen a lot of work being presented of how to address this, and a lot of people have a very clever idea of how to do this, especially now that we have LLMs at our disposal. We have an ever-growing body of knowledge on this. One of the problems that remain is that we don't have a reliable way to do cross-study comparison, because at the moment, all the paper I could read, everyone is creating a small data set, a small evaluation metric, and report its own number on its own approach, and we have no idea how the different methods compare to one another. And in order to enable this cross-study evaluation, we need two things. We need a shared data set, which is open and everyone can use it, and this we have provided already last year and keep extending over the course of the year. So currently we have more than 40 BIM models there and more than 1,000 question-answer pairs. And the second one is a systematic evaluation protocol, because we cannot use any of the deterministic metrics like bleu, rouge, or something like this. They are poorly suited for this work. And earlier this year, we have introduced an evaluation framework as the GNI symposium. So it's not the focus of this work, but to present it very briefly. On the left side, we have the question style. So the questions are categorized. It's a taxonomy inspired by the work of Hellin and Eastman from the code compliance check. And we have 4 categories of questions to try to identify how difficult they are. And this is based on where the data is located. So we don't analyze the question by itself, but where we have to dig into the BIM model to find the relevant information. And this is used also to determine for the evaluation criteria what is allowed as a data source for answering some of the question. So moving from the question to the evaluation criteria, so on the answer level, we have defined 5 evaluation criteria, binary, so that can be answered by yes or no, or not applicable. First one being abstention, so that gates all of the other. It is possible, and in our view, recommended for a model to abstain to answer to a question if it cannot find the required information into the BIM model instead of hallucinating anything. So we treat this differently as a raw correct answer or wrong answer. If the model decided to answer the questions, then we analyze if the answer is faithful, so is it grounded in actual data inside the BIM model? Is it complete, transparent, and relevant? And I refer to the paper for more detail on this. In order to test now our proposed framework for automated evaluation, we needed also to have a BIM-Qa system to generate answers that we could then evaluate. For this, we reused what we have presented last year again. So this is a pretty simple LLM loop that we have. So based on the React framework, which stands for reasoning and acting. How it works, a user is sending a question related to a BIM model. These 2 inputs are brought into a system, which starts a loops, sending API call to an LLM, and the LLM is trying then, based on the question, to retrieve the information needed to answer it, using some a library of tools that we set to a disposal. It calls the tools with the necessary argument. The code is being, or the tool is being evaluated with a Python interpreter. The result fed back to the LLM, and this continues on and on until the LLM thinks he has all it needs to answer. And then instead of outputting a tool use, it's outputting the final answer, which is then fed back to the user. So now the actual focus of this paper, the experimentations that we have done. So using the presented system and the mentioned data set that we had before, we have generated again a couple of answers to the provided question from IFC-Bench. And we had 2 evaluators, human evaluator, to analyze or to grade them with this evaluation framework being uncoordinated. So they didn't have the chance to talk with each other. They got the same piece of paper explaining the criteria, and they were trying to answer. And as you can see here, although we have a good raw agreement, we have 89% agreement, we have a pretty poor iterator agreement of 0.43 of Krippendorff alpha. So it's partly because reviewer did not agree on the criteria, and also partly because the system is already pretty good, so most of the answers were correct, so we have a limited pool of questions with incorrect results, and that drives a higher Krippendorff alpha. So this is all baseline, two uncoordinated humans. Now, what happens if we bring LLMs into the game using the LLM as a judge paradigm? We can see two things here. The first one is that LLMs are much more consistent with one another than uncoordinated humans are. Doesn't mean that they are right, just that two completely different LLMs agree. And for this, we took two different backbones of a very different origin. We had Gemini 3.1 Pro from Google, so a closed US-based model. And we had the GLM 4.7, so an open source from the Chinese lab ZAI. So two different LLMs from two different continents agree quite a lot. And more interesting, they actually agree with each individual human more than the two humans, uncoordinated human, with each other. So we are still not reaching the tentative threshold of 0.66 for Krippendorff alpha, but we are still getting closer to it. Now, what happens if we give the human a chance to talk to each other and go through the answer together, again with evaluation criteria, and speak things through and see if they can see eye to eye, if they have a chance to discuss. And here, that's what we can see here on the most right column. Humans do agree very much with one another if they have a chance to discuss, talk things through. With this 0.92 Krippendorff alpha, it means that we only had two criteria on which we eventually did not agree on. And also very interesting, now we can see that our LLMs actually also agree even more with this consensus, so this human consensus, that they did with the two different humans, this time because they are coordinated and their answer or evaluation collapse into one ground truth, we could say, for this evaluation, or at least the human version of the ground truth. And it's very, very narrow, but we are reaching this, on average, this tentative threshold with 0.68, but the range is quite wide, so it depends on the criterion that we have. Now, what are the takeaways that we can take from this study? So the first is that the framework we have introduced is actually validated, because if humans have the chance to discuss it, they actually agree on the result, on the evaluation. But the problem that we have is that when we don't have the chance to coordinate with one another, we actually don't agree that much. So probably the, let's say, the introduction to the framework, giving more example, more work should be done, maybe for humans to have more preparation and be able to grade things similarly, even though they can't align. What we have, which is probably the most interesting of this study, is that the LLM as a judge actually outperforms this uncoordinated expert. And if we are being realistic, that's the reality that we have. Different research labs won't have the opportunity to meet and sit together and go through hundreds of questions and decide together what's the best way to evaluate it. So we will stick to our baseline of two uncoordinated human experts for this. And we have seen that this LLM as a judge actually outperform these uncoordinated humans. So if we want to have a higher level, let's say, of a cross-study comparison, it's not perfect, but it's actually our best option at the moment to use LLM as a judge. And the nice thing is that we get automation for free, because believe it or not, analyzing all of these questions or all of these answers, is a pretty tedious process. So if an LLM can do it for us, and we can iterate very quickly on this work without having to review manually all of this answer every single time, that's actually a pretty nice thing. And the last point is that it seems to be LLM agnostic. We only tested two backbones, so I don't want to overclaim, but we were able to test two completely different large language models, and they do align very much with one another. We obviously still have a couple of limitations. We only had two human judges, both co-authors of the study, so yeah, might be not perfectly neutral. It was a relatively small sample. We didn't run it through the whole IFC-Bench, only on 74 question-answer pairs. And the overall inter-rater agreement is still not that great. We are just reaching this reliable or tentative conclusion, and not the reliable conclusion. And with this, I would like to thank you for your attention and not going to the beach earlier, and I will do my best to answer your question if you have any.